Now we're going to quickly go over different types of symmetry. We're going to go over symmetry with respect to the x-axis, y-axis, and origin. So I have the definitions here. And I think it's because my math lab asked you a question over it. Maybe it doesn't. Not 100% sure. But here's the definition of symmetry with respect to the x-axis. A graph is symmetric with respect to the x-axis if for every point x, y on the graph, the point, and you can see here from our graph, the point x, comma, negative y is on the graph. So if this is my graph right here in red, let's say that this point here is at 4, 1. Then over here, we're still at the x of 4, but now we're down 1. And so you can see here on this graph, we are symmetric to this line of our x-axis. So if a graph is symmetric with respect to the x-axis and the point 3, 2 is on the graph, then the point 3, negative 2 is also on the graph. I don't know if this is going to help or not. But think about it if you have a heart. And let's pretend that my heart is perfect. I'm human, so it's not perfect. But let's just pretend that the left side of this heart perfectly mirrors the right side of this heart. So if this graph was something like this right here, this would be a graph that is symmetric. The top would mirror the bottom according to this x-axis line right here. So by definition, it needs to be that every point x, y on the graph, there's the point x, negative y. But for me, just look visually. Does it mirror this x-axis right here? So similarly, symmetry with respect to the y-axis. Next lesson, we're going to refer to this as an even function. A graph is symmetric with respect to the y if for every point x, y on the graph, the point, and you can again see over here on the graph, for every point x, y on the graph, we have the point negative x, y on the graph. So if this point here was maybe 5, 2, now this point would be over negative 5, but still up that same y of 2. So if a graph is symmetric with respect to the y-axis and the point 3, 2 is on the graph, then the point negative 3, 2 is also on the graph. But again, just look visually. This is your definition that every point x, y, the point negative x, y is on the graph. But to me, does it mirror this y-axis? So again, if my heart is perfect, you have that y-axis going right through the middle. So now the left side is going to mirror the right side. Okay, and then we have an odd, with symmetry with respect to the origin. And next lesson, we'll call this odd function. A graph is symmetric with respect to the origin if every point x, y on the graph, and you can again see from here, the point negative x, negative y is also on the graph. So if this point here, or let's say this point here is maybe 1, 3, then we have the point negative 1, negative 3. So if the graph is symmetric with respect to the origin, the point 3, 2 is on the graph, then the point negative 3, negative 2 is also on the graph. So by definition, every point x, y, there's a point negative x, negative y. But visually, what does that look like? And I like to just say that if you turn your page 180 degrees, it looks the same. So this one would not apply. This would not have origin symmetry because if you flip this upside down, now that looks different. But here, you can see it goes up, it swoops down and goes another point. If you flip it, it does the exact same thing. It swoops up or goes up, swoops down, and then another point right here. It looks the exact same. So from last video, this circle right here would have origin symmetry. If you took this, flipped it upside down, that looks the exact same. So just turn your paper 180 degrees. Does it look identical?